Dear students, in this video, I'm going to start error, stability, and convergence of single step methods. So we will discuss this topic. So before going to start this topic, the first definition is well-posed initial value problem. So what is a well-posed initial value problem? So the initial value problem, say dy by dx is equal to f of xy with initial condition y at x naught is equal to y naught, which is defined in the domain this x is varies from x naught to some constant b. Both are constants. So this is basically the original problem. So this problem is said to be well posed if first condition, a unique solution yx to the problem exists. That means this problem has a unique solution. Second condition, for any epsilon greater than 0, there exists a positive constant k depends on epsilon such that whenever epsilon naught magnitude is less than epsilon and delta x is continuous with condition that magnitude of delta x is less than epsilon on this interval, that means this closed interval x naught to b, then a unique solution zx to the perturbed problem. This is the original problem, this is the perturbed problem, and the problem is this: dz by dx is equals to f of xz plus delta x with initial condition z at x naught is equal to y naught plus epsilon naught. That means this problem is well posed if we get this unique solution and satisfied, and under these conditions this perturbed problem also has a unique solution, and the condition is what? The initial condition has this error, because here we have y naught, here we have y naught. This is the error introduced in the initial condition, and similarly this is the error which is introduced in this equation. So when we introduce some error here, then we will get this perturbed problem. Okay, so this is the perturbed problem, this is the actual problem. So if this problem is well posed, then this solution has a unique solution, and this perturbed problem under these conditions is what? The error, this error is bounded. Similarly this error in the initial condition is also bounded. When both are bounded, then this perturbed problem also has a unique solution. So this solution exists with this condition, magnitude of zx minus yx. That means the difference between the unique solution of this and the unique solution of this is less than k epsilon, k depends on epsilon, multiply by epsilon. Okay, so basically this is k into epsilon. Here this shows only that k depends on epsilon. So this is, if so, then we can say that this problem is well posed. So what is the condition? Condition says that this problem is well posed if this problem has a unique solution. Second, when we introduce some error here and some error here, that means we will get a perturbed problem. Then this perturbed problem also has a unique solution under these conditions. Conditions are what? This error introduced in the initial condition is also bounded, as well as the error introduced in the differential equation is also bounded. So both should be bounded. Then we will get a unique solution exists, and the distance between the unique solution of the actual problem and the perturbed problem, this should be also be bounded. That means k into epsilon for all x in the interval x naught to b. Okay, so this is double star equation, this is star. So double star defines a perturbed problem associated with the original problem star. The perturbed problem assumes the possibility of an error delta x, that means this is the error, being introduced in the differential equation, as well as an error epsilon naught, this being presented in the initial condition. So this represents the error introduced in the initial condition, and this also represents the error which is introduced in the differential equation. Fine. So that's why this is known as perturbed problem. So what is the note? Note is that numerical methods will be concerned with a perturbed problem, since any round of error introduced in the representation perturbs the original problem. Okay, so care must be taken to ensure that the original problem is well posed. So whenever we are dealing with any problem with numerical methods, then that problem should be well posed. Otherwise, there is no guarantee that a numerical solution to the perturbed problem will approximate accurately the solution of the original problem. Okay, because using numerical method we are trying to find out the approximate solution. So if problem is well posed, then we will reach towards the accuracy by applying the numerical methods. However, if the problem is not well posed, then what will happen? We may get a very different solution from the exact solution. Exact solution is different and we will get approximate solution which is far from the exact solution. तो यानी जो solution हमें ऑब्टेन करना चाहिए था, हम कुछ और ऑब्टेन कर लेंगे बाय अप्लाइंग न्यूमेरिकल मेथड्स. तो एक्चुअल सॉल्यूशन के क्लोज जितना जा सकते हैं तभी वो न्यूमेरिकल मेथड सक्सेसफुल होगा. एंड दिस विल ओनली हैपन इफ द प्रॉब्लम इज वेल पोज्ड. अगर वेल पोज्ड प्रॉब्लम होगी तो हम न्यूमेरिकल मेथड से जो सॉल्यूशन ऑब्टेन करेंगे वो एक्यूरेट सॉल्यूशन के लगभग काफ़ी क्लोज होगा. ओके, दिस इज द मीनिंग. So the condition that ensures that an initial value problem is well posed are specified in the following theorem. So how to detect that the problem is well posed? Because always using this is the general definition obviously, but for every problem if you are applying this definition, then this may be difficult to find out that whether the problem is well posed or not. ये तो definition है. तो अगर आप डेफिनेशन को अप्लाई करके वेल पोज्डनेस चेक करेंगे सो दैट मे बी सम टाइम डिफिकल्ट. तो हमें एक कंडीशन चाहिए कि ये कंडीशन अगर हो जाए तो हम कह दें कि यस प्रॉब्लम इज वेल पोज्ड. सो नाउ दैट इज द कंडीशन. सो दैट्स व्हाई दिस इज द थ्योरम विच विल प्रोवाइड यू अ कंडीशन. सो व्हाट इज द थ्योरम? सपोज डी इज द डोमेन having the points of the form xy where x varies from a to b and y is basically from minus infinite to infinite. That means the entire y-axis. This is the entire y-axis. So this is the domain. So if f is continuous, this function f is continuous and satisfies a Lipschitz condition. So what is the Lipschitz condition? We will discuss it later on. So if f is continuous and satisfies a Lipschitz condition in the variable y, very important, variable is y here, on the set D, then the initial value problem, this dy by dx is equal to f of xy, y at a is y naught, where x varies from a to b, is well posed. That means what is the condition? That function should be continuous and satisfies Lipschitz condition in this domain. Then we will say that this differential equation is well posed. Very important condition. तो हमें क्या चीज़ें चाहिए कि फंक्शन कंटिन्यूस होना चाहिए, सेकंड लिप्चिट्स कंडीशन को सेटिस्फाई करना चाहिए विद रिस्पेक्ट टू वेरिएबल y. तो अब ये लिप्चिट्स कंडीशन क्या है? लेट्स सी. दिस इज द लिप्चिट्स कंडीशन. सो व्हाट इज दिस? सो लिप्चिट्स कंडीशन. सो लेट f of xy be a continuous function of x and y for all xy in domain D, and let x naught y naught be an interior point of the domain D, and assume that f of xy satisfies the Lipschitz condition. So assume that function satisfies the Lipschitz condition, then this condition holds. Magnitude of f of xy1 minus f of xy2, this should be less than equal to k times magnitude of y1 minus y2. This is valid for all points xy1 comma xy2 in domain D for some constant k greater than equal to 0, where k is basically given by this constant. K is equal to maximum of magnitude of the value del f by del y, where maximization is taken on every point xy in the domain D. Xy belongs to D. Okay, so this, using this you can find out the constant k, and if this condition holds, then we will say that uh, Lipschitz condition is satisfied by the equation. So if function satisfies this Lipschitz condition and f is continuous, then we will say that our equation is well posed. So now here we have taken one example, and this example is basically checked that the problem is well posed or not, and we have applied both the approaches. First, we will identify that the given problem is well posed or not with the help of Lipschitz condition. Second thing, we will introduce some error in the initial condition as well as in the differential equation, and then identified whether the given equation is well posed or not. And here we have applied the definition. So basically we will identify whether the problem is well posed or not using two methods. One with the help of Lipschitz condition, and second with the help of the definition. Okay. So first we will apply the well posed Lipschitz condition. So what is the condition? Condition is that first you identify the constant. So domain is xy, where x varies from 0 to 1 and y varies from minus infinite to infinite. Okay. Now the equation is dy by dx is equal to y minus x square plus 1. This should be 2. I think this should be 2. This should be 2. Okay, this should be 2. So now dy by dx is equal to y minus x square plus 1, where x varies from 0 to 2 and y at 0 is 0.5. So this is the equation. So what is your f? F is basically this, y minus x square plus 1. So now first find out the constant k. So del f by del y will be what? According to this should be 1. Now find out the magnitude. So magnitude of 1 will be 1. So obviously according to this, since this is a constant, that's why the maximum of this value is also 1. That's why k should be 1. So also fxy, which is y minus x square plus 1. So you can see that this is basically a polynomial type equation. So that's why this is continuous. So we will say that f satisfies a Lipschitz condition. This condition is satisfied in y because Lipschitz constant exists. Okay. So satisfies a Lipschitz condition in y on domain D with Lipschitz constant k is equal to 1. Since f is continuous in domain D, because function is, I am saying that this is a basic polynomial type. So since f is continuous on D, then by the previous theorem, the initial value problem is well posed because we will have a Lipschitz constant. So Lipschitz condition is satisfied. Function f is also continuous, and hence by the theorem problem is well posed. Now we will discuss the same problem with the help of definition. So to discuss with the help of definition, first we will introduce some error in the initial condition herein as well as in the differential equation. So when we introduce some error herein, so the variable is now z in place of y. dz by dx is z minus x square plus 1. So in place of y we have replaced z. So z minus x square plus 1 plus error is delta. Domain is as it is same, 0 to 2, and here the condition is z at 0 is 0.5, this value, plus some error epsilon naught. So here some error is introduced, here is some error is introduced, and y is replaced by z. So we will get the perturbed problem. Okay, where delta, this, and epsilon naught both are constants. Now the solution to the actual problem, this, the solution of the actual problem is, say dy by dx is y minus x square plus 1, y at 0 is 0.5. So when you solve this problem with the help of, because this is a linear differential equation, you can easily solve this problem. That the solution is yx is equal to x plus 1 whole square minus 0.5 into e raised to the power x. Now when you solve the perturbed problem with this initial condition, then the solution is this. So this is the perturbed problem, and the solution is zx is equals to x plus 1 whole square plus delta plus epsilon naught minus 0.5 into e raised to the power x minus delta. So this is the solution for the perturbed problem. Again, this is basically obtained very easily with the help of linear differential equation. We can solve it. Similarly, this is the solution for the actual problem. This is the solution for the perturbed problem. So now let us assume that this delta, this error is bounded. So magnitude of delta is less than epsilon. Similarly, this error is bounded. Magnitude of epsilon naught is epsilon. Okay. Now we will find out the difference between these two. So magnitude of zx minus yx minus zx is equal to. So when you take the difference, then term is cancelled out with this term. Okay. This minus 0.5 e raised to the power x is cancelled out with minus 0.5 e raised to the power x. So we will get only this term into e raised to the power x minus delta. So this is the resultant. The magnitude of delta plus epsilon naught e raised to the power x minus delta. Now apply the triangle inequality. So this should be less than equal to the magnitude of this term plus magnitude of this term. So that's the magnitude of this term into e raised to the power x. And since the domain is basically this, so the maximum value of e raised to the power x is obviously obtained at point 2. That's why e raised to the power x less than equal to e raised to the power 2. The maximum value should be of e raised to the power x in this domain is e raised to the power 2. So that's why this is less than equal to magnitude of delta plus epsilon naught e raised to the power 2 plus magnitude of this quantity. Okay. Now according to this condition, magnitude of delta is less than epsilon. So here we will have epsilon. Okay. This is epsilon. Epsilon naught is also less than epsilon. So epsilon plus epsilon is 2 epsilon. So 2 epsilon e raised to the power 2 plus this is also less than epsilon. So plus epsilon. So when you take epsilon common, so we will get 2e square plus 1 into epsilon. This is for all x. Okay. So ultimately we will see that by the definition, if you will see this was the definition. So this should be less than some constant k, depends on epsilon into epsilon. So here we will get this difference is less than equal to this constant k multiplied by epsilon. So since we will get this constant k, that's why what is k epsilon here? This is the k epsilon. Okay, and hence we will say that problem is well posed because we will get this constant k. If we does not get this constant k, then we will say that the problem is not well posed. Okay, so that's why we will basically check the problem with the help of two methods. One with the help of Lipschitz condition. So in Lipschitz condition, we have only to find out the constant k. If this constant exists, then we will say that if this constant exists, then Lipschitz condition is satisfied. Then we have to identify the second condition, that function is continuous or not. Since herein function is continuous, Lipschitz constant exists, then by the previous theorem, problem is well posed. Now the same problem is discussed with the help of well posed definition. So here we have introduced the error in the differential equation as well as some error in the initial condition, and then we have find the solutions both for the exact solution and for the perturbed problem solution. Then take the difference, and if this difference is less than equal to some constant k into some epsilon, then we will say that the problem is well posed. Okay, so this is the well posedness. Okay, so I think for today this is more than sufficient. In the next lecture we will discuss about the study of error in a numerical method of initial value problem. Okay, thank you.